welcome to the chemistry class. Today we are going to discuss colligative properties. So, what is the meaning of colligative properties? See here, the properties which depends upon the number of the solute particles. The properties which depends upon the number of solute particles. Those are called as colligative properties. See here, whatever the nature of the solute, that does not matter, it will not going to affect. Only we are considering the number of the solute particles. It means how much a solute is added to the solvent, that contributes to the colligative property. So, what is the meaning of the colligative property? The properties which depends upon the number of the solute particles. So, those are called as colligative properties, and keep in mind that they are going to ask you the definition of the colligative property. Define colligative property and write any one of the colligative property, or give one example for the colligative property. See here, there are 4 colligative properties. Those are, first one is relative lowering of the vapor pressure of the solvent, and second one depression of the freezing point of the solvent, and third one elevation of the boiling point, and fourth one is osmotic pressure of the solution. So, all these are very important, and we are going to study all these colligative properties in detail. Okay. So, the meaning of the colligative properties, the properties which depends upon the number of the solute particles. So, those are called as colligative properties, and there are 4 colligative properties are present. In that, today we are going to study about the first one, that is relative lowering of the vapor pressure. Relative lowering of the vapor pressure. So, in our one class I have said you the relative lowering vapor pressure is the ratio of the lowering of the vapor pressure with the vapor pressure of the pure component. Okay. So, let me discuss this in detail. So, let us consider a solution which is a pure solvent, which is a pure solvent. Here there is, in a container we are taking the pure solvent, and as it is only pure solvent, at the surface the solvent molecules are present. At the surface the solvent molecules are present, and this pure solvent is volatile in nature. It is volatile in nature. It means the particles of the solvent will going to form the vapors, and that vapor will going to exert the pressure. Here there is a formation of the vapors. Okay. And these vapors will going to exert the pressure. That is what we called as vapor pressure of the component in the pure form, that is P1 naught. Clear? So, for this pure volatile solvent, I am going to add a non-volatile solute. I am going to add a non-volatile solute. So, let me take this one is a solution which is consisting of non-volatile solute plus pure volatile solvent. Okay. So, when I am adding a non-volatile solute, it means it will not going to be escape from the surface. Keep in mind that here when we are adding a non-volatile solute to the pure volatile solvent, what happens? The surface is not only covered by the solvent particles, it is also covered by some solute particles. See here, this mark, whatever I am doing, let me take this as solute particles. Along with the solvent particles, there are certain solute particles will going to occupy the surface. So, what happens, as the solute particles will going to occupy the surface, they will not going to escape from the surface. but the solvent particles will going to escape from the surface, those number will going to be reduced. Those number will going to be reduced because some of the particles are solute particles. Clear? So, here also there are formation of the vapors, but these vapors are less in number. These vapors are less in number. Why these vapors are less in number? Because the surface is also covered by the solute particles. The surface is also covered by the solute particles. So, only few of these solvent particles gets converted into vapor, and those will going to exert the pressure. That pressure I am going to take it as P1. I am going to take it as P1. So, I hope you are getting what I am explaining. Here I am taking the pure solvent and the surface is covered by the pure solvent particles or molecules, and those will going to escape, and those vapors will going to exert the pressure, that is the P1 naught, because it is in the pure form. And next I am going to add some amount of the non-volatile solute to the solvent. During that time what happens? The surface is covered by the solute and solvent particles, but in that the solute particles are non-volatile. They will not going to escape, they will not going to produce the vapor like that. Okay. While the solvent particles can have the ability to get escape from the surface, but that number is reduced because some are solute particles which are what we can say, those are also covered the surface. So, here also formation of the certain vapors, and those vapors will going to exert the pressure. That pressure I am going to take as a P1. That I am going to take as a P1. Obviously, when you look at these two, you can able to say that P1 naught is greater than P1, because the pressure exerted by the pure solvent is more than the that of the solution, because here solute molecules will going to inhibit that effect that much. Okay. So, let me go for the relative lowering of the vapor pressure derivation. So, whatever looking this, we can say that lowering of vapor pressure, lowering of vapor pressure, okay, that is I am going to take delta P, that is I am going to take as delta P. So, delta P is equals to P1 naught minus P1, P1 naught minus P1. So, lowering of the vapor pressure is the difference in the vapor pressure of the pure solvent and that of the solution. Okay. So, I have the expression that delta P is equals to P1 naught minus P1, P1 naught minus P1. Since we know that according to Rolle's law, according to Rolle's law, I will change one term here. Let me take P1 as P1 naught as it is, and instead of P1 I am going to take P1 naught into x1. Am I correct? According to our Rolle's law, what it says, P1 is directly proportional to x1, that is P1 is equals to P1 naught into x1. So, I am going to take here the value of the P1 as P1 naught into x1. So, here P1 naught is common, 1 minus x1, 1 minus x1. Okay. And then one more thing, we know that the sum of the mole fraction is always unity, the sum of the mole fraction is unity. Now, x2 is equals to what happens, x2 is equals to 1 minus x1, x2 is equals to 1 minus x1. So, I am going to substitute 1 minus x1 term as x2. So, delta P is equals to P1 naught into x2. Okay, what we are talking? We are talking about the relative lowering of the vapor pressure. See here, relative lowering of the vapor pressure is the ratio. It is the ratio of the, that is the lowering of the vapor pressure with the vapor pressure of the pure component. So, relative lowering of vapor relative lowering of vapor pressure, that is delta P divided by P1 naught is equals to x2 is equals to x2. Now this I am going to write as delta P is nothing but P1 naught minus P1. Delta P is equals to P1 naught minus P1, and keep P1 naught as it is, P1 naught as it is, okay. And then here x2 I am going to take it as, what is x? X is nothing but mole fraction. So this I am going to write as N2 divided by N1 plus N2. Are you getting what I am telling? X2 is equals to N2 divided by N1 plus N2. Now, delta, that is P1 naught minus P1 divided by P1 naught is equals to N2 by N1 plus N2. This is our expression which we got. But for a dilute solution, what happens? We are going to take solute is less while solvent is more. So always keep in that whatever the calculation come here, you have to remember the numbers. One number is always for solvent and number 2 is for solute. As we are telling here, solute is very less. In the denominator term, you have to skip this term, that is for dilute solution N2 is less. N2 is less. So what happens? P1 naught minus P1 divided by P1 naught is equals to N2 divided by N1. Because solute is less, I am going to skip this term. So what happens? N2 by N1 for the dilute solution. So here again, what is N2? Number of moles. N is nothing but number of moles. So number of moles formula is mass divided by molar mass, okay. That is W divided by M. So P1 naught minus P1 divided by P1 naught is equals to N2. It means W2 by M2. That N2 I am here, if you want I will write M2, and N1 is equals to W1 by M1. So I am going to substitute W2 M2 and then here divided by W1 whole divided by M1. So what happens? It will goes to the upside and here it will be the W1. W2 into M1 divided by M2 into W1. So this is the expression for the relative lowering of the vapor pressure, relative lowering of the vapor pressure. Okay. So, once again I will tell you derivation part. Lowering of the vapor pressure, that is indicated by the delta P. Lowering of the vapor pressure is indicated by the delta P. Delta P is equals to, we know that according to this one, P1 naught minus P1. Okay. The lowering of the vapor pressure can be defined as, it is the difference between the vapor pressure of the pure component with the vapor pressure of the solution. So, sometimes they are going to ask you the definition also. Okay. And then delta P is equals to P1 naught minus P1 we have, and according to our Rolle's law we know that P1 can be written as P1 naught into x1. So, I have substituted instead of this P1 as P1 naught into x1, and then P1 naught is common in these two terms. So, what else remained in the bracket? 1 minus x1, but according to the mole fraction concept, x1 plus x2 is equals to 1, x2 is equals to 1 minus x1. So, I am going to take it as x2. Now, we need to know the derivation of the relative lowering of the vapor pressure. So, what we are going to take? We are going to take the ratio, that is delta P divided by P1 naught, that is the ratio of the relative lowering of vapor pressure is defined as the ratio of the lowering of the vapor pressure with the vapor pressure of the pure component. Okay. And then this is equals to x2. Again delta P is nothing but P1 naught minus P1 divided by P1 naught. X2 is equals to what? X2 is equals to N2 divided by N1 plus N2. Okay. So, that only I wrote here one more time, but N2 is very less as compared with the N1, because in our solution chapter, whatever the problematic section is there, you have to take the number 1 for the solvent which is larger and 2 for the solute. Okay. And for a dilute solution, what happens? N2 is very lesser as compared with the N1, solute is less as compared with the solvent. So, that term is left out. So, that what happens? P1 naught minus P1 is equals to P1 naught is equals to N2 divided by N1 term remains. Now, N2 is nothing but, that is N2 or N1. N indicates what? Number of moles. We know the formula that number of moles is equals to mass divided by molar mass, that is W by M. Then if I wrote for the respectively 1 and 2 components, that is for solute and solvent, you are going to get N2 value as a W2 by M2 and then N1 value as a W1 by M1. So, if I substituted here N2 and N1 value, that you are going to get that P1 naught, lowering of the vapor pressure value, that is P1 naught minus P1 divided by P1 naught is equals to W2 into M1 divided by M2 into W1. So, this is how we can derive the expression for the relative lowering of the vapor pressure. So, in our next class, we are going to discuss certain problems on this law. Okay. Thank you. So, let us discuss one problem on the basis of the relative lowering of the vapor pressure. Here, the vapor pressure of the pure benzene at certain temperature is 0.850 bar. A non-volatile, non-electrolyte solid weighing 0.5 gram is added when it is added to 39.0 gram of the benzene. The vapor pressure of the solution then is 0.845 bar. What is the molar mass of the solid substance? See here 39.0, that is 39 gram of the benzene is the solvent, and they are adding 0.5 gram of the solute, and they have given the vapor pressure of the benzene in the pure form and the vapor pressure of the solution, and the question is that to find out the molar mass of the solute which you are adding the solid substance, that acts as a that's molar mass we need to calculate. So, let me write the given terms. Here, the vapor pressure of the pure benzene, that is vapor pressure of the pure benzene P1 naught is equals to 0.850 bar. A non-volatile solute of weighing 0.5 gram, it means that is the weight, how much, 0.5 gram. Whether it is a solute or solvent, it is the solute. For solute, we are going to take the number 2, and then when added to 39 gram of the benzene, that is also weight, that is 39 gram, that is W1, because 1 is for the solvent. Now, the molar mass of the benzene they have given, it means solvent's molar mass is 78 gram per mole. And the question is, and one more thing they have given, the vapor pressure of the solution then is, it means vapor pressure of the solution is P1 is equals to 0.845 bar. The question, we have to find the molar mass of the solid solute, that is M2. So, according to our relative lowering of vapor pressure, P1 naught minus P1 divided by P1 naught is equals to, the formula is there, W2 into M1 divided by M2 into W1. Okay. So, substitute the values here, P1 naught minus P1 is 0. Divided by P1 naught is same 0.850, W2 is 0.5 and M1 is 78, and then M2 we need to calculate, sorry, into W1 is 39. Okay. How I am substituting? From the given, I wrote all the terms and we know the formula and we applied that and we substituted all the values, and you need to calculate here M2. Separate out the term M2. M2 here, M2 is equals to 0.5 into 78 divided by 39. If it goes here, this will be cross multiply into divided by 845. So, if you simplify this one, you are going to get the value as 170 gram per mole. So, this is the molar mass of the solid substance which they have added, that is M2, and the unit must be, you have to mention, the molar mass is gram per mole. So, this is how we can solve the problem on the basis of the relative lowering of the vapor pressure. So, next question. Here I am not solving the problem, I am giving this one for you only, and I will tell only the problem similar to this problem, similar, only they have exchanged the values, and this was asked in your annual examination. So, let me tell the question. Vapor pressure of the pure benzene is 200 millimeter of the mercury. Okay. Pure benzene they have mentioned. Then you look at the term whether it is P1 naught or P1. Pure they have mentioned means P1 naught. And then when 2 gram of the non-volatile solute is dissolved in 78 gram of the benzene, it means they have mentioned the 2 gram solute weight, W terms they have given. in 78 gram of the benzene. W1 and W2 values they have given, and P1 not also given, and benzene has the vapor pressure of the 195 millimeter of the Hg. See here, this is the vapor pressure of the solution, and calculate the molar mass of the solute. Again here also you need to calculate M2. You need to calculate M2. Okay. So given, write the whatever terms they have given first as like this given, then write the formula, substitute all the values and separate out the term M2. Finally you are going to get the answer, and always mention your answer with respective units. Okay. So molar mass is expressed in terms of gram per mole. If they have asked any pressure, means you have to express that in terms of bar. So like this we can able to solve the problems on the basis of the relative lowering of the vapor pressure. Okay. We are going to continue one more colligative property in our next class. Thank you.